Hello, everyone. My name is Mark Wong. I work for Second Quadrant. I'm going to give a little presentation on some of the patches that have been proposed for 9.6, now that 9.5 is in alpha, and focus primarily on the ones that are expected to help the performance of Postgres. So that's really the background of it, and then I'll go into some of the patches a handful of patches I've selected for this to show some numbers with. Describe the tests a little bit to give you an idea of hopefully how this might relate to the kind of things you're doing on your own systems and what the results look like. All right, so who's heard about this parallel sequential scan patch coming out? Anyone try it? Nope. How about unique joins? Fixed decimal data type? Postgres XL? How many people are running on mainframes, on IBM mainframes? So anyone thinking about it? All right, so I'll show some numbers to see if it piques any interest and everyone can see what Postgres on a mainframe looks like. So the parallel sequential scan is authored by Amit Kapila. Feel free to let me know if I mispronounce anything. He's at EDB. There's also a companion patch with that involves assessing parallel safety in the back end. That's authored by Robert Haas in EDB. The purpose of this is to improve the performance of a sequential scan on a table where the number of rows you're going after are relatively small to the total number of rows in the table. So one of the configuration parameters this patch adds is a parallel seq scan degree to limit the number of processes that will work on a parallel sequential scan. So a couple of limitations. At the moment, it will only work on select statements and statements that don't have joins in them. The unique joins work is authored by David Rowley at Second Quadrant. The purpose of this is to help queries where the inner side of a join is known to be unique, and known to be unique because there's a unique index on that column being joined, a group by clause, or a distinct being used. The fixed decimal data type is also authored by David Rowley. At the moment is being provided by an extension, so this isn't really just new for 9.6. It will work on 9.5 and earlier. I'm not sure how much earlier, but something that isn't going to be unique to 9.6 unless it gets added as one of the primary data types. So the intent of this is to improve performance of queries that are aggregating many rows of numeric data. It does this by using 64-bit integers to provide a predefined precision decimal, similar to numerics, where numeric is a selectable precision decimal. And one other thing to note under the covers is that excess precision with this data type is going to get truncated as opposed to rounded. Now, Postgres XL, for those of you who are not familiar with it, is intended as a scale-out Postgres solution. If you're familiar with the Postgres XC or Staudo projects, many of the people who are involved in those are also involved in Postgres XL. In this particular case, this isn't really against 9.6. The work of Postgres XL is being applied to the 9.5 branch at the moment. So with the IBM Z systems, we're not really looking at new patches to try on these on the mainframe. Just really a little evaluation of OLTP performance on the hardware. We'll see how it stands compared to a popular competitor. And in this particular case, this is also really a 9.6 thing, where they wanted to look at the current release, which is 9.4 at the moment, just to get a feel of where they stand compared to the other hardware vendors out there. So I'll go over the tests a little bit first before we get to the results. Everyone heard of pgbench? So pgbench is a TPC-B derivative, considered a database stress test, resembles some OLTP-like transactions, something analogous to electronic data processing, batch processing. And it measures the performance of things by how many transactions you can run per second. So how many people have heard of the TPCC? Yeah, so most of these that I look at are mostly TPC derivatives. So for those of you who heard about the TPC, familiar with the C? The C is an online transaction processing benchmark. It's centered around activities of an order entry system. And how performance is measured here is by seeing how many transactions you can execute per minute. Now, how many of you heard of the H? So the H is emulating a part supplier data warehouse, and this benchmark measures how fast you can create a data warehouse, how fast you can get your data in there and create indexes. And it is also intended to give you an idea of your query processing power. How many of these queries can you run? How fast you can run a predefined set of queries. Transactions with multiple SQL statements. All right, parallel sequential scan. What I've done here is just I basically repeated some of the things that Harry Babu at Fujitsu Australia had already posted to the hackers mailing list. I wanted to show a few more data points just to illustrate some of the trends of how this parallelism works. I used one of the tables from the TPCH, which is the line item table, the largest table in that database. And we will vary the selectivity of the rows coming back by basically using a modulo against the order key column, since the artificial data being created for these benchmarks are known to be sequential and without gaps. So to give you an idea of the data of this table, a 100 gigabyte size TPCH database, where the line item table is the largest, will have 600 million rows-ish, a little more, I think, and takes about 80 gigabytes of space on disk. How many people is this going to be large for? Anyone have bigger databases with bigger tables? So to give you an idea what this table looks like, 16 columns, 4 integers, 4 numeric values, a couple characters, a few dates, a few strings. The system that I ran some of these little tests on is an AWS EC2 system running Red Hat Enterprise Linux 7. This particular one is the i2 4X large type, 16 CPUs, 122 gigabytes of RAM, 4 800 gigabyte SSDs. And to give you an idea of what the query looks like, pretty basic. We're just selecting one of the key columns, doing a modulo on it. A couple of the things I just wanted to point out, you can set the parallel scan degree is how you would limit the parallelism that is used for executing this. And also just wanted to mention the CPU tuple com cost variable is what the planner uses to determine whether it's appropriate to use a parallel plan. And it's by setting it to 0, we're basically telling the planner that, oh yeah, I need sequential scan, it's always going to be cheaper to run it in parallel. And the reason for this is just to illustrate some of the trends and show why it might be important that this parameter is tuned properly. So here's a chart, got 3 trends on here. The red line is selecting 100% of the rows. That first number with 1 backend, it's basically the baseline. And just to show, if you're trying to use a parallel sequential scan on a table to retrieve all its rows, it's probably not the best idea. The response time actually more than doubles in that case. But then when we start to dramatically reduce the number of rows coming back, selecting 25% of the rows, when using 2 processes to parallelize that execution, reduces the response time by 25%. So that looks pretty good. But unfortunately, by selecting only 25% of the rows back, it looks like using any more than 2 processes to parallelize that is starting not to look so good again. Then on the bottom line, where we're selecting about 12.5 of the rows back, using 2 to 4 processes to parallelize that reduces the response time by about 40%. And with the higher selectivity, it looks like there's some potential to have greater gains with more backends parallelizing the query. So we like to think that the parallel sequential scan is something we could look forward to for cases, as obviously more work is going into the patch. A lot of discussion on the mailing list. So with the unique joins, the results I'm presenting here have been conducted by Thomas Vondra at Second Quadrant. He designed a simple test here where he's using a simple fact dimension type join where he has 10 times more fact rows than dimension rows to see what we can expect from taking advantage of this. So just to give you an idea, a dimension table that he created, integer primary key column, fact table that he used has a foreign key set with the reference to that primary key. Query is pretty simple. He's just selecting all rows that come back from joining those 2 tables on the key. The system that he tried this on was a single socket Intel system running CentOS 7, 8 cores, 16 threads, 64 gigs of RAM, a couple of SSD drives. And this is what he found. With 100,000 rows in a dimension table joined against 1 million factor rows, he saw a 7% improvement. With 1 million dimension rows against 10 million factor rows, he saw a 17% improvement. And even at larger tables, or a larger number of rows, he was able to see a 10% improvement with 10 million dimension rows versus 100 million fact tables. Anyone have more data in their tables? So clearly with this patch, while it seems that there's a good benefit from it, there also appears to be a sweet spot of where people are going to see the most returns from this. Some of this fixed decimal data type. Do people here deal with a lot of, what's the word, monetary type data? So what we did here to look at this was to take another look at, was to use the TPCH benchmark. Just take a look at the power test. And in trying to see what we could expect before running the tests, one of the queries does run on just this line item table. And in this line item table, the 4 columns I highlighted, if you may have noticed that they were reals earlier. But since this fixed decimal data type is intended to replace a numeric, well, not replace numeric, but to be a better option for financial money type of numbers than numeric. So 4 of the columns here are candidates to see if using a fixed data decimal type will be a good win for us. To give you an idea of what one of the queries is, query 1 in the TPCH is designed to report the amount of business done, billed, for shipped and returned items. So simple description is the majority of this query is doing an aggregate of sums and averages on pretty much various combinations of those 4 numeric columns over a given ship period, grouped by the whether it's been returned and what the line order status is. So here are what the results look like. Just a bar chart was showing each query, what the response time was. The color on the left, the light blue, is the response time of the query where numerics was used. In all the tables, we changed all numerics to use this fixed data decimal type. So the blue number, the blue column is just showing what the results are with the numerics, and the purple for the fixed decimal types. So we see 4 out of the 22 queries seem to show a pretty substantial improvement. Query 1 that I just showed is showing a 55% improvement. Query 14, 63, query 18, 46%, and query 20, 34%. Doesn't seem to really have a significant impact for any of the other queries in this benchmark. So it seems to be pretty clear if you have queries if you have a database where you have numerics for representing money, financial related type data, that if the fixed precision of this data type is acceptable, you should be seeing some good gains with any queries doing a lot of aggregates against those columns. So now for Postgres XL. what we looked at here, we looked at the load and power test again, and we wanted to see how it performed against 9.5. I was able to grab some numbers against 9.5 Alpha 2 against the head of the current development branch of the Postgres XL stuff. So again, we'll take a look at the 100 gigabyte databases. For those of you familiar with Excel, you know you can design how many data nodes, where your coordinators are, and transaction managers are. So what we initially came up with was to build a 8-node cluster with an additional node that's running the global transaction manager and a coordinator that we will run all the queries through. And then the 8 other nodes are just data nodes with a GTM proxy on them. So we did this with EC2 systems again. We used the little i2 X large types that have only 4 processors, 4 virtual CPUs, 30 gigabytes of memory, and one 800 gigabyte SSD drive. For the system we used to compare to 9.5, we basically took a system that was 8 times as large. Thought that might be a good place to start a little comparison. So it has 8 times as many processors, 32, 8 times as much RAM, 244 gigabytes, and 8 times more SSD drives. So here are what some of the numbers, or some details on the load test. With 9.5, Alpha 2 took about 2 hours to load. A couple of things to note differently with XL was that we took the data files and split them 8 ways, same number of data nodes that we had, and loaded all of those simultaneously through the one coordinator we had. And in doing that, the load time was reduced down to 44 minutes. And this load time also includes the index creation. So the index creation isn't necessarily seeing the same sort of gains from splitting up the data files to load separately. Turns out to be 63% faster. And we believe that there's more room for improvement. We did a pretty basic approach on loading this. We feel that if we were to create an additional coordinator per data node that we have and take those data files instead of splitting them systematically, that if we split those data files to match the type of distribution method that is being used between the data nodes and send those off to the different coordinators, we think that there still might be still a more substantial change to how fast we can load data into PGXL. But we have yet to give that a try yet. So for the power test, similar chart to before showing the response times for all of the 22 queries. It seems pretty clear across the board that PGXL is able to execute a lot of these queries much faster than 9.5, except for one or two cases. It seems to be roughly the same. And in terms of scoring in the benchmark, the score for 9, the increase in the score for PGXL is almost 160% more, greater. So then, just to repeat a couple of points, the loading data seems to be good on using comparable number of resources, and being able to execute ad hoc decision support type queries. So now onto the mainframe, giving some new hardware a spin. The one detail out. IBM released the Z13 earlier this year. The processors on this thing can be clocked up to 5 gigahertz. The size system that we looked at was just 8 cores, 16 threads, 64 gigs of RAM. Might be interesting to note that you could load one of these mainframes up to have about 140 cores in the system and up to 10 terabytes of memory. So we did this on RHEL 7 and again on Postgres 9.4. So as you may guess, I may not necessarily be able to disclose what we ran this up against, but if you think of a popular competitor, we try to pick the same sort of things on there. Although this single socket system only had 8 cores, 16 threads, the clock speed of the processor was just 2.4 gigahertz, and then using the same 64 gigabytes of memory. So on this, we just really looked at those OLTP type benchmarks, PGBench and a TPCC. With a TPCC, we didn't really run it in the traditional sense. We didn't have the really comparable storage in this case, so we ran these tests to be like all in memory, see how fast and how many transactions we can run against this thing. So it's purely measuring the processing power of the systems. And what we see here with the IBM system put up against their popular competitor, it seems like they are able to process almost 2 times, 1.7 times, more transactions per charts per number of clients, and how many transactions those number of clients are able to execute. So between this 0 and 80 number of clients, it's the average, the percent increase seems fairly consistent. So on some of the simpler tests, the PGBench, the 4 lines we're showing here is to illustrate how both systems look with threading disabled or enabled. As I think it's still a popular question. People worry about the performance of systems with CPU threading these days. Does anyone still tend to turn those off on your systems? Leave them on? So the bottom number is the popular competitor with threading turned off. Do you get some marginal gains in this read-only scenario when turning on the threading? So then with the IBM mainframe, comparing the 2 lines where threading is turned on for both systems, we're able to see about that we're able to run twice as many read-only transactions. So just to illustrate another, the other end of that read versus write spectrum, when running a simple write-only test with PGBench, the popular competitor, the performance, whether you had hyperthreading on and off, there was some pretty minimal difference. They show up as the same line on this chart. Whereas the Z13 mainframe, having threading turned on and off on that system, showed a fairly substantial gain, and compared to the other system, we're also able to see about twice the number of write transactions. So that's all the data I had to show. A couple of other patches to point out that I wasn't able to show data for this presentation. There is other work to improve the query of statements that are aggregating lots of data. Work from that is being done by David Rowley. There is some additional concurrency work being done by Jeff Janes around the heap, so that the general transaction performance in MVCC is able to scale better. Peter Gagan, if you heard him talking if you heard his lightning talk yesterday, talked about some of the sorting changes that he's been working on that I think some have been committed, some additional ones have been proposed that are being considered for 9.6. There's some work that has begun from Thomas Vondra and Alvaro Herrera to implement a column store, an open source column store. And then an array of additional CPU scalability work being done by Andres Freund. If you saw his presentation, he talked about some of that work that he's been doing. Others who help on various ways, other patches, include Robert Haas, Ahmed Kopla, and Simon Riggs. And how many people use a lot of PostgreSQL stored procedures? So Tom Lane has, I think, already committed a patch where it stored procedures that are using a lot of variables. There was substantial gains to be made in those cases because of improving the way that the stored procedures is passing data back and forth with the executor. So lots of stuff that I hope people are looking forward to in the future to make their systems run faster. Thank you for listening. Yes? Yes, that's correct. For the parallel seek scan, it currently will only work with select statements and select statements that aren't joining tables.
So that means if it's any view that has joins in it, you still won't parallelize?
Yeah, right.
What was the second part of your question?
Just if you get a view that has joins.
But what if you've got a CTE that's only that table and then join that with something else?
Yeah, I see the reason. I see the reason for why you would ask that if having this in a CT, and I'm afraid I don't know the answer to that. But yeah, I think that's a good question. Yes?
On the Excel benchmark for loaded data, did you split the following ways
For 9.5? Yeah, I did experiment with that, and I think it's because it's an EC2 system and not really having. I think with more performance storage, I might see some gains, but even splitting it in half to load 2 copies, I didn't see anything worthwhile enough to share. Yes?
On your Excel benchmark as well, did you consider using more than one data node per instance on an I2 XOR?
Yes, we did. And the reason I can answer the yes to we consider it. The reason why I don't have much data is I actually didn't have enough time to explore the different possibilities. But certainly that is a consideration to have, how many data nodes to run on a single system.
Yeah,
And
we found the same thing with saturated core,
right,
running multiple on the same
right,
storage.
right. Yeah, right. Because it's pretty clear that you look at each individual node and you can see how they're not fully utilized, right? Yeah. Yes.
Okay, actually about the parallel scan, what can be the use case for doing sequential scan for highly selective queries? Like why, like I would say like when you need highly selective queries by not doing index, what use cases you had in mind when you cannot deal with index and still need like highly selective queries?
Yes, good question. I might need to ask for help. The question was use cases for when you would have highly selective queries. I'm afraid I don't have too much practical experience, but
So,
if,
like, rule of thumb is like create index when you actually need to, execute highly selective queries on this field. So
Yeah.
That's why I'm wondering why it can be even like, I mean, if you guys included it, it definitely was some request, some demand, and something.
Yeah.
I'm just curious why.
I think there are several reasons for and against, and for one that I am a little familiar with creating an index. For very large tables, and very large being tables that are approaching 1 terabyte and larger, the B-tree indexes are not practical to have, and
So we're talking about these size of tables. Makes sense.
yeah, yeah, and that's about the extent of my experience. Any more questions? All right, thank you, everyone.